In this video, we are going to model Bernoulli's equation. This can be shown using a simple structure made out of a straw and 2 cups filled with water. However, for a more biomedical and less boring example, this can be used to mimic what happens during a cerebrospinal fluid (CSF) leak or a spinal headache. The top cup represents the cranial cavity. This is where the brain is, and it is surrounded by cerebrospinal fluid. The bottom cup represents the end of the spinal cord, and the straw represents the dural space, a piece of connective tissue that holds the spinal fluid. Now let's see it on a person. Let's call this guy Steve. He just had an epidural, but the doctor went a little too far and nicked the dural space, and now has a leak. As Steve is standing, the loss of spinal fluid makes his head really hurt. When he is lying down, he has more fluid in his cranial cavity, which makes him feel better. Luckily, Steve was able to get a blood patch to seal the leak and is reaccumulating his spinal fluid and healing well. But now we can look at Bernoulli's equation to explain this. V1 equals 0 meters per second squared, as fluid in the cranial region moves very slowly, and the density of spinal fluid is 1,000 kilograms per meter cubed. P2 equals atmospheric pressure, and H equals Z1 minus Z2 as the vertical distance between the brain and the leak. These simplifications simplify our equation. We can look at this when lying down and standing. When lying down, the vertical distance between the brain and the leak is small. So let's choose 0.05 meters as the distance. We can calculate the pressure using our simplified equation of P1, atmospheric pressure, is equals to rho times G times H. When plugging in our constants, our density of spinal fluid and gravity constant, we then get the exit pressure. We can then calculate the exit velocity by taking the square root of 2 times G times H. So when lying down, our pressure on the brain is 490.5 pascals, and our exit velocity is 0.9905 meters per second. Now let's look at standing. When standing, the distance between the brain and the leak is larger, so let's have H be 0.25 meters. The pressure in the brain is calculated the same way, and we then get 2,452.5 pascals. We can then calculate the exit velocity, which is 2.214 meters per second. Now let's look at what happens at the leak when standing and laying down. When standing, more fluid is exiting the body quicker than when laying down. While lying down, the vertical distance between the leak and the brain is smaller. This leads to a lower pressure and a lower velocity. The fluid will then leak out of the body slower. The body can then keep up with a minor leakage and maintain stable intracranial pressure. When standing, the distance between the brain and the leak is larger because gravity pulls the column of CSF downwards, and the opening represents a path of least resistance. The increase in H means the potential energy decreases, and therefore the static pressure decreases, which causes the brain to sag and create severe pain.